Hi, welcome back. In this video, we're going to talk about transformations by looking at the equations and the graphs. In the previous video, we spoke about the effects and the changes of the letters A, B, H, and K, when specifically focusing on a quadratic. So we looked at the quadratic function, and we focus on what happens when we change A, B, H, and K. As I mentioned before, these letters are applicable to any parent function. That is a cubic function, absolute value, square root, cube root, all of the functions that we've spoken about before, right? All the parent functions. The only thing that would change is, for example, the square function would then change into a square root. Yeah? The A is still in front of the function, B is inside, H is attached to the X, and the K is on the outside. And I can do this for cubic functions. I can change it to pretty much any function that I want. Notice how the A, B, H, and K are all there. Well, today we're going to focus on equations to do more examples of the variations of the different parent functions and different graphs. How do I look at a graph and identify whether it's been compressed, stretched, whether it's been moved to the left and right or up and down? So let's get to it. Here we have a quadratic and we have an absolute value. Right? I can always, if I'm able to recognize the shape, I'm always able to graph the function itself. I can always graph f of x equals x squared, and I can compare it to this one to see how it moved. Now, all parent functions, for the most part, are going to go through the origin and cross at 1 over 1, meaning this. They're going to start at the origin, or centered at the origin, and go through the point 1, comma 1. Now, I went through that on the previous video explaining how we get points on the graph. Same thing here for the absolute value function. It's going to be centered at the origin, and it's going to go through 1, comma 1. 0, 0. Here we have 0, 0, and 1, comma 1. I showed in the previous video how to graph those and how to identify that. So the first thing that I look at is that since the function is not at the origin, I already know that this moved 1, 2, 3 units to the right and 1 unit down. Yeah? So I can describe that shift. The function shifted 3 units to the right and 1 unit down. And I can tell that because it should have been centered at 0, comma 0. It should have been pointing up here. Now, how do I know if it was stretched, compressed? How do I know that? Well, if this was the origin, the graph would have gone over 1 point to the right. Right? This is 1 unit to the right, 1 unit up. So from this point, the vertex, which is 3, negative 1, it should have been over 1, up 1. It should have looked something like this. The parent function. So what happened? Now, visually, I can't really tell you specifically if this was a vertical or a horizontal change, right? Whether it's A or B that's being affected. But I can describe both situations so we can see which one it could be. When we get to the examples of equations, we'll know exactly which variable was affected, A or B. But for now, we're gonna use our visuals to compare them. So vertically, this point landed up here. When I moved 1 to the right, I ended up going higher than I expected. That point was moved up. So I call that a vertical stretch. Yeah? This is a vertical stretch. function got narrower. Now, if I'm trying to describe the horizontal changes, notice how horizontally the graph went inward. That point went inside. So horizontally speaking, I could say, or this is a horizontal compression because I squeeze the function inward. Yeah. How would I describe the absolute value here? Well, the parent function, if I want to compare it, is the absolute value of x. You could graph that and you can see how it should have started at the origin, but instead it moved 1 to the right and 2 units down. The vertex, this starting point, tells me how it was moved. This is 1, negative 2. So it moved 1 from 0 and down 2 from 0. So I can say the function shifted 1 unit to the right and 2 units down. What about the stretching and the compression? Well, from the origin or from the vertex, it should go over 1, up 1. Over 1, up 1. The function should have looked like this. I'm going to use the parent function as my reference point. That's the only way to know whether or not it got stretched or compressed. So vertically speaking, this point ended up being lower than I wanted it to be. I was expecting it to go up 1 over 1, but it went a little bit lower. So vertically, what's happening here? What is happening to these points if it's going lower? They're going lower than expected, so we call these a vertical compression. Because I'm squeezing the graph downward. Horizontally, what's going on with the points? Well, notice how the points, this line is actually going to be wider than I anticipated. Right? If we remember our hands, the function starts here, and it's going wider outside. So we are doing a horizontal stretch. Again, it's really hard to tell whether it's A that's affecting the function or whether it's B that's affecting the function. Sorry, in this case, B would be inside. Right? And the only way to find out is by looking at the specific equation, which is why for these scenarios I use the word or. Because this could be a vertical stretch or a horizontal compression. And here we can be compressing it vertically or stretching it horizontally. What about this function? Here we're dealing with a square root function. So the parent function is the square root of x. I know that it should have started at 0, 0. But instead, it starts at 2, 1. So the horizontal change, I already know that it shifted, the function shifted 2 units to the right and 1 unit up. How do I know if this was compressed or stretched vertically, horizontally? Well, from the center, I'm going to be able to go up 1 over 1. Right? The majority of our functions behave that way. So this one should have gone through here instead. Instead, the point happened to be graphed lower than I anticipated it to be. What does that mean vertically? Vertically, we are compressing it. This is a vertical compression. Or horizontally, what's happening? Horizontally, this point is getting pulled outward over here. So since we're squeezing it vertically, we're also pulling it outward. We're doing a horizontal stretch, right? This is going further out. horizontal stretch. Again, we're using the parent function to compare everything. Well, what do we expect it to be? We expected this to be at 0, 0, and to go through this point. Instead, it moved up and to the right, and instead of going up at 1 over 1, it went lower. So that's a compression. Now let's get to the specifics. Let's look at an equation. As you can see here, we have two equations. We have an absolute value, which creates a V, and we have a cube root, which creates this like slanted S kind of looking shape. The original function, right, the most basic form of this equation, if I remove A, H, and K, the most basic form is the absolute value of X. I could always graph the absolute value of X and compare it to see the changes visually. Here, the most basic form is the cube root of X. If I graph both of them, I can compare them and see the changes visually. Ideally, we slowly pull away from the graphing and we get to the understanding of what's happening, right? So let's identify these variables. In general, this is the A value, B, X minus H, plus K. As you can see here, the A value is negative 1/2. A affects everything vertically. The negative, this is a vertical change, right? Vertical transformation. The negative tells me it reflects the function vertically. So reflects over the x-axis, right? A is doing everything vertically. So this is going to flip the function into the negative direction vertically. What does the 1/2 do? Well, the 1/2 is a compression, a vertical compression. Notice how there's no B value here. Multiplying it times 1 doesn't do anything. So there's no horizontal stretch or compression happening here. And then we have H and K. Notice how we're doing X minus H. The H value is a positive 1. We're subtracting positive 1. And then the K value is a negative 2. What does that mean if the vertex is at 1, negative 2? It means it moved 1 unit to the right and 2 units down from the origin. So instead of starting at 0, 0, like this function moved 1 to the right and 2 units down. At the same time, it's getting reflected vertically, it's getting flipped upside down, and it's going to be a vertical compression, so it's going to be wider. So the function will look something like this if I were to graph it. All right, let's take a look at the cubic function. Identify the original points or the variables, right? This is A cube root B X minus H plus K. What does this 2 do to the function vertically? It's positive, so it's not flipping over anything. But this 2 is a vertical stretch. Yeah, because it's bigger than 1. This B value happens to be a negative 1. So note, remember how B affects the function horizontally? These are all the horizontal changes happening, right? So if it's negative, it's going to flip horizontally. What does that mean? It means that it's going to flip or reflect over the y-axis. The y-axis is vertical. So if the function flips this way, right, we are reflecting it over horizontally over the y-axis. What happens here with H and K? Well, what do I have to plug in here so that a minus, the number changes it to plus, right? Minus and negative. That means that H must be a negative 1, right? What happens if I do X minus negative 1? It turns into plus 1. which tells me h must have been a negative number. And then k, we have a -2. What does this tell me for the origin or for the center of the graph? It means that it got moved 1 to the left and 2 units down from the origin. Right? The idea here is to identify the most basic parent function of what's given and then identify the variables. And if you need to graph these, you can graph these functions and you can compare it to the parent function. That way you can visually see how we were talking about earlier. You can see if it was stretched or not. Now, gradually, what we want to be able to ultimately do is use the general function notation. Notice how here, I don't have a square root anymore. I don't have an x squared. I don't have a cubic or a cube root. I have a general function f. So if I have a general function, what does this 1/4 do? What does this negative do? What does this value and this value do to any specific function? Well, I know a is going to exist in front of the function. B is going to be existing on the inside. H is going to be with k, right? We have x minus h, and then we have a plus k at the end. So whatever function this is, I know that a is 1/4. So this tells me this is a vertical compression. Right? What does the b do? Well, b deals with all horizontal changes. We're going to reflect this function over the y-axis. Because it's flipping horizontally, right? The h and the k value here are 2, 1. What does that tell you? It tells you that it got moved 2 units to the right and 1 unit up from the origin. It doesn't matter if this is for any function, right? This could be replaced with a square root. It could be replaced with a cube root, a quadratic, anything you want, right? For any given function, what changes occurred? Feel free to practice with these other ones. I'm going to walk you through them as well. Here I have the a value being negative. B is 1/3. You have x minus h, and then plus k. So since a is negative, we're going to do a reflection vertically, right? So a vertical reflection over the x-axis. B is 1/3. Now, how do I remember the effects of b? I think about a. I know that when a is greater than 1, this is a vertical stretch. When a is between 0 and 1, right, those fractions like 1/5, 1/4, 1/3, 1/2, this is a vertical compression. Well, b, the horizontal changes are always inversely related. So if we're doing a vertical stretch for b, the value is going to be the inverse relationship, right? So for b, we're dealing with a horizontal compression. And here, for b, when it's a vertical compression, b is going to be a horizontal stretch. So when a whole number greater than 1 stretches the function, a whole number would compress the function. Right? So if b is greater than 1, we're doing a compression. Now, if a fraction between 0 and 1 compresses it vertically, a fraction, right, between 0 and 1 would do a stretch. So this 1/3 is the opposite of a compression, vertical compression. So we're dealing with a horizontal stretch. This is a horizontal stretch. Right? If I do the inverse, 1/3 flips to 3/1. The 3/1 is a stretch, right? Now, what is our h and k? If we're dealing with x minus h, that means that this one must have been a -1, right? X minus -1 turns into +1. So h is -1, and then k is a -2. So this function got moved to the left and down 2 units. All right. This problem puts everything together. You're welcome to pause these videos and try them yourself, and then press play to see if you got the same answer right. Here I have a, b, x minus h plus k. So the negative 1/2. This is a vertical compression and a reflection over the x-axis because it's negative. So it's flipping over the x-axis and it's compressing it. The b is flipping it over as well, but over the y-axis. And the 3, right, since it's bigger than 1, it's a compression. So this is a horizontal compression and a reflection over the y-axis. What is our h and k? H must have been -2, and k was +1. X minus -2 makes it a +2. So this moved 2 to the left and 1 unit up from the 0, 0, from the origin. I hope this has helped. Feel free, right, to graph the general parent function so you can visually see it, but eventually, hopefully, as you practice this more, you can start doing these for any given function, any f. Right? A, B, H, and K. It doesn't matter if it makes a V, a U, a square root, an S. It doesn't matter the shape. The changes are the same. I hope you guys are having a good day. Don't forget to like and subscribe. And as always, we'll calculate.